Hello everyone, so in this section we want to review the inverse of exponential functions, logarithmic functions. So let's start with a definition. Again, for every base of exponential functions, there is a specific inverse logarithmic function. So we're going to start off with given a base greater than 0, similar to the way that we did for exponential functions. And also b cannot be equal to 1, but I'm just not going to write that down. The logarithm with base b is written y equals log base b of x, and is defined actually as the exponent in another equation. So if you have y equals the log base b of x, the equation that also must be satisfied is b to the y is equal to x. So this is just a double arrow. That came out so bad. I want to fix it. Probably not going to do any better, but we'll give it one more shot. That looks a little better. Okay, so let's look at evaluating these things. One way to think about evaluating them is we can just answer the question, b to what power gives x, or gives the input. So obviously you can evaluate these things by just plugging them into your calculator, but by trying to evaluate them by hand, it gives you a better understanding of how these things work, what is a reasonable domain, and what inputs you are actually able to compute. So for A, let's try to evaluate the log base 5 of 25. So how would we think about this? Well, basically that's all you have to do is answer the question, 5 to what power makes 25? And if you can do that, then that's the answer to this, or that's the numerical value of this logarithm. So the answer here is just 2. If we continue and we look at another one, let's say b, let's suppose we have the log base 7 of 1 divided by 343. Again, you're answering the same question. 7 to what power makes 1 over 343? And the answer here is going to be actually -3. And just to reason that out a little bit further, 1 over 343 is the same as 1 divided by 7 to the third, and that is the same as 7 to the -3 from our laws of exponents. So when you ask that question, 7 to what power makes 1 over 343, it should be now clear that that is -3. If we look at another example, let's say the log base 8 of 1. Well, for this one, this is going to be equal to 0 because any non-zero number raised to the 0 power equals 1. In particular, 8 to the 0 power is equal to 1. So we're kind of just translating this logarithmic equation into the exponential equation that it corresponds to. Okay, here's one. Let's look at the log base 12 of -1. This one is actually going to be undefined. If you raise 12 to any power, no matter what that power is, it's always going to be a positive value. I don't care if it's a negative, it's positive, anything. So for that reason, any log of 0 or any negative number is not defined. If you look at our exponential functions, they always had a y value that was bigger than 0. So let's just make that comment down here. The log of 0 or any negative number is not defined. So the domain of any logarithm are just going to be the positive values. So the only inputs you can plug in there are positive numbers. Okay, so let's talk about some notation because there are two special logarithms that come up. So the notation, the two most used logarithms are written with their bases understood. So the first is the common logarithm. So that's what it's called, but that's not the notation. So the common logarithm is just written y equals the log of x. So there's no base written anywhere. And what that means is the base is actually 10. So it means the base is 10. We also have the natural logarithm. And because you can make the base any positive number, this is actually quite a strange base you might think at first, but it's going to be very important when we start talking about the derivative and the antiderivative. And actually when we start looking at continuous exponential functions like in previous sections. So y equals the natural log of x, so we just write ln of x. This actually means the base is Euler's number, e. So the main means the base is exactly e. Again, let's just remember e is 2.71828, so on. So it continues forever and does not have any pattern because it's an irrational number, or it does not repeat. So let's look at some examples where we just evaluate these. Same deal. Just trying to do them in our head without using any calculator. So let's say we have the log of 1,000. Well, basically we're asking 10 to what power is equal to 1,000? Well, powers of 10 are easy because you're just counting zeros. So 10 to the third power is 1,000. B, let's look at the natural log of the square root of e. Well, remember the square root of e is the same thing as e to the 1/2. So this is the natural log of e to the 1/2. So the answer here is just 1/2. We could also look at maybe the natural log of 1. Well, e to the 0 power will also equal 1. So this is just equal to 0. And d, let's say we did the log of 1 over 100. Well, 100 is 10 to the second power. So to do the reciprocal, we would just make that the negative exponent. So this evaluates to -2. Okay, so let's look at some corresponding graphs. Again, there's basically two principal shapes to these graphs. So graphs of logarithms. So whereas exponential functions go to infinity the fastest, these logarithmic functions, they still go to infinity, but they actually go to infinity the slowest. And we'll see why that is maybe when we look at the limit section. But for now, let's just try and understand their shapes. So y is equal to the log base b of x. This is what we're trying to graph. So we can consider the same two cases. Those are going to give the two shapes when b is greater than 1 and when b is between 0 and 1. So the first shape roughly looks like this. So this happens when b is greater than 1. So maybe we'll go to Desmos and take a look at the y equals the log base 2 of x. Maybe we'll look at that graph. And then the second one, we could look at maybe log base 1/2. So this happens when 0 is less than b is less than 1. So for example, y equals the log base 1/2 of x. So let's go over to Desmos and have a look at that. So I need to put a comma there. All right, so let's look at y equals the log base 2 of x. And we see those things. Notice that all the powers of 2, we're going to find nice y values, nice output values. So at an x value of 2, we get 0. Oh, sorry, that's 1. At 1, we get 0. At 2, we get a y value of 1. At 4, which is 2 squared, we get a y value of 2. And if you went all the way over to 8, we get a y value of 3. Similarly, if you go to -1, we get a y value of 1/2. -2, we get a y value of 1/4, and so on. But let me zoom out to show you how slow this goes to infinity. If you go out far enough, it actually looks like it's kind of forming a horizontal line. But actually, if you go far enough to the right, you can get any y value as large as you want. So say you wanted a y value of 100. That's all you'd have to do is plug in 2 to the 100th power. And just to get our shapes, let's go ahead and do y equals log base 1/2. Let me just put 0.5 of x. And again, we get that same shape. So notice, whereas the exponential graphs were kind of reciprocals when we looked at 2 to the x and 1/2 to the x about the y-axis, these graphs are reflections about the x-axis. Okay, so that's it for the graphs. We're not going to spend too much time there. We're going to start looking at properties, and one of the reasons these logarithms are so important for us is they allow us to solve exponential equations. So what are the properties of exponents? Or properties of logarithms. They, in fact, come from the properties of exponents. So I'm not going to write any base down here, but these properties work so long as the bases match. So the first one is the log of m plus the log of n is equal to the log of m times n. So that could be natural log of m plus natural log of n equals the natural log of m times n. As long as the bases involved are all the same, you can do this. Again, that's going to be similar to the property, so we kind of have a correspondence here from our exponential rules. So you can use the one to prove the other. So the first exponential rule is actually if you do a to the m times a to the n, this is equal to a to the m plus n. So we kind of see that sum to product being similar there. The next one is the log of m minus the log of n. This is equal to the log of m divided by n. And this would be similar to the exponential rule, a to the m over a to the n is equal to a to the m minus n. And then 3. This third one is probably the most used property in terms of solving equations. So if you have some power inside the parentheses, you can bring it out front in terms of multiplication. And this actually corresponds to this exponent rule. A to the m raised to the n is equal to a to the m times n. All right, so let's go ahead and look at how these can be used to solve equations. And maybe we'll add, before that, just the inverse properties, because maybe those aren't so clear, but they do arise naturally. So let's do the inverse properties before we start talking about solving these equations. There's also inverse properties. So the inverse properties are as such. Basically, if you have the log base b of b to the x, this is equal to x for any x, because b to the x will always be positive and won't cause any problems in the domain of the log. And we also have b raised to the log base b of x. This is equal to x, but because x is the input of the logarithm and the exponent there, this is only true for x greater than 0. So kind of in particular, things that come up a lot. So let's say in particular, so we have the natural log of e to the x is equal to x, and e to the natural log of x is equal to x. And also, if you did the log of 10 to the x, you would get x, and 10 raised to the log of x would come out to x. In those second properties, again, that's only true for positive values of x, but I just wanted to highlight those are, since we're commonly just using log and natural log, those are the ones that we recognize most frequently. So let's go ahead and jump back and start solving equations. So maybe we'll kind of divide the paper here as well. All right. So let's go ahead and go for this example. Let's say we want to just solve for the unknown, and we start with a 10 is equal to 3 raised to the 2x plus 1. So if you had an equation like this, anytime you recognize an unknown in the exponent, that's when you want to take logs of both sides of the equation. So let's just do common logarithm. So if you do the log of 10, that will be the same as the log of 3 to the 2x plus 1. But we know the log of 10 is actually just equal to 1. For the right-hand side, what we want to do is we want to bring that exponent of 2x plus 1 down. And this is by log property, or did I call it rule? I probably called it rule if we go up. So log property. Log property number 3. Okay, so a lot of times for these, students tend to get confused if I just leave the logs in the entire time. So what we'll go ahead and do now is just approximate that log of 3. Again, that's just a number, so this just becomes a linear equation. So I can say, okay, 1 is equal to 2x plus 1. It's really important to keep those parentheses around that, times log of 3 is about 0.477. Again, I'm using a little rounding here, but that's okay. So let's take 2x times 4.77, and we get 0.954x plus 0.477. And then that is just a linear equation that you can go ahead and solve. And solving it just amounts to subtracting 0.477 and dividing by 0.954. So your answer should come out, well, I'll go ahead and do the steps for this one, since it's the first one. So we're subtracting 0.477 to isolate the term containing the x. So we have 0.523. This equals 0.954x. Then we divide by 0.954. And what do we end up with? We end up with x is about 0.55. So let's continue. Let's do another. So the harder version is when you have two bases where none of them are if you have like 10 somewhere like we did in this one, you can take logs and one side should simplify nicely from the inverse property. Or if you have e, the other side should simplify nicely. But let me see. No, we don't quite have enough room. Or if you see an e, you can use natural log and one of those sides should simplify nicely. But let's say you had something like 5 raised to the 3 minus 4x equals 7 to the 9 plus x. Well, things are more complicated then. It doesn't really matter which log you use. but we have to take log of both sides. But nothing's going to cancel. So what we're going to do is we're just going to use that property 3 again, and then just go ahead and evaluate. So let's go ahead and bring those exponents down. So we get 3 minus 4x times the log of 5. And then we get 9 plus x times the log of 7. So then what do we have? Well, we have 3 minus 4x times 0.7, and that will equal 9 plus x times 0.85. Okay, so then like before, let's go ahead and distribute on both sides of the equation, and collect x's on one side and regular values on the other. So we get 2.1 minus 2.8x distributing the 0.7, and on the right we will end up with 7.65 plus 0.85x. So I'm choosing to move the x's to the right hand side, so we'll add 2.8x to both sides, and we end up with 2.1 is equal to, well, actually we can do this all in one step. Let's go ahead and do it all in one step, because might as well save some space. Since I'm moving my x's to the right, I might as well move my regular numbers to the left, so I want to subtract 7.65. So I end up with minus 5.55 equals 3.65x. And we just divide on both sides by 3.65. And if we approximate x, it's about negative 1.52 there. So quite a few steps, but really once you apply the properties of logs, everything simplifies to a linear equation. So there's not too much craziness there. Let's go ahead and go the other way. So let's say we have the argument trapped inside a logarithm. Can we solve that? So we're going to have to use the inverse properties the other way. So again, still we want to solve for x here. So solve for x. So let's say we have the log of 5x minus 1 is equal to 2. So what we want to do is we want to exponentiate both sides with base 10. So we want to make both of these sides exponents of 10. Why do we want to do that? Remember, 10 will cancel with log if the log is in the exponent. So on the left here, we just end up with 5x minus 1, and on the right, we have 100. So solving that, we just get x equals 101 over 5. Nothing too complicated. Let's say b. Let's suppose we had the natural log of 7x plus 3 equals 0. Again, this is not so difficult. We're just going to use the other inverse property. So if we make both sides the exponent of e, then we will be able to cancel out that logarithm. And we'll just be able to evaluate on the right. So on the left, we'll have 7x plus 3, and on the right, we'll have 1. So, I mean, if you want to say right here, we could say that this is by inverse property number 2 in both problems. And then solving this one, we end up with x equals negative 2 over 7. So if you have what's known as a logarithmic equation, you're going to have to use the second inverse property. Let me go ahead and highlight one other interesting example that will show the difference of where the exponent is in both of these equations. So let's think about solving the natural log of x quantity squared. So this means natural log of x times natural log of x versus the natural log of x squared. So this would mean the natural log of x times x. Well, which side can you use inverse, so exponent logarithmic property number 3 on. You can use that on the right-hand side to bring the 2 outside. The left-hand side, you can't really do that on, though. So the left-hand side, we just have to leave as is. And on the right, we can bring that 2 out in front. So by log property number 3. And then what we can do is we can actually go ahead and subtract 2 natural log of x on both sides. And the reason that is interesting because now we can actually factor. So we end up with the natural log of x times the natural log of x minus 2. So this is actually a quadratic equation in the natural log of x. So it relates to our polynomial examples that we looked at. Well, then we can just set each equation equal to 0 and solve. So we either have the natural log of x is equal to 0, or the natural log of x minus 2 is equal to 0, which is the same as the natural log of x equaling 2. Well, then what you can do is you can just basically make everybody a power of e. And we see that x has to either equal 1 or x is equal to e to the second power. And again, that's by inverse property number 2. Okay, so let's go ahead and look at an application example, and then we'll call it a day after that. We'll look at more of these things in the future once we start looking at rates of change and the derivative. Anyway, so a lot of populations in the short term will grow according to exponential equations and models. So let's go ahead and look at that. So suppose P of t is equal to 437.2 times 1.036 raised to the t power. And let's suppose this models the population of a country and thousands of people and I actually just looked at my notes. I believe this is for a county, not a country. So let's say county. It doesn't really matter. T years since 1995. So that's a data alignment notion. So if you say T is years since 95 or T is years after 95, that just makes the numbers smaller and the model more reasonable. So let's say T equals 5, that just means the year 2000. And if you had a year, say like 2010, you could just do 2010 minus 1995 to see that T is equal to 15. So let's say, when will the population reach 1 million? Excuse me. So what we want to do here is we want to write down our exponential equation. So 437.2 times 1.036 raised to the t. We want to write what that's equal to. We're given a population number of 1 million. Well, remember the population is in thousands of people. So 1 million is actually 1,000 thousands, right? Because if you did 1,000 times 1,000, that's 1 million. So this is the equation we need to solve. So we start by dividing both sides by 4. 37.2. And we're left with 1.036 to the t power is equal to, let me just write this down as a decimal, 2.28728. If you punch that into your calculator, then just take logs of either sides and apply the properties to solve. I'm going to use natural log You can use common log, it doesn't matter. I like to use common log for writing because it's one less letter, one fewer letter. So it's more efficient to write. Okay, so from log property number 3, we can bring that exponent out. So we get t. I'm not going to approximate this time. I'm just going to leave the logarithms there and approximate the last step. So again, whenever you have the input of a log is just a regular number, it's just representing a numerical quantity. It's nothing fancy. You just don't know what the numerical quantity is because these things are hard to evaluate without a calculator. So if we divide by the natural log of 1.036 on both sides, we will have solved for t. So we have t is approximately 23.4. Okay, so since it's a word problem, we should answer the we should have the final answer as a sentence. So again, if you do 1995 plus 23, you would get 2018, and if you did 1993 plus 24, you'd get 2019. So basically, this is telling us that we're hitting our population goal sometime between 2018 and 2019. So we expect the population to reach 1 million and we'll just write down 2018 to 2019. And that is it. So that's a quick overview of logarithmic functions, their properties, and definitions and graphs. So this is Dr. Lennon signing off.